Hello everyone, my name is Yash Yadav and my enrollment number is DE2402298 and I am a student of International Institute of Professional Studies and the subject is Numerical Analysis and Design and this is my video presentation for second assignment. So let us begin. Section 1 which is about finding roots of polynomial equations. First is bisection method. This is one of the simplest and most reliable root finding techniques. The basic idea is if a continuous function changes sign between 2 points, then a root must exist between them. So in the code, we first check whether f of a is multiplied by f of b is negative or not. If it is positive, then there is no guaranteed root in that interval. Next, inside the loop, we calculate the midpoint. C equals a plus b divided by 2. Then we evaluate f of c. If the function value at c is very close to 0 or the interval becomes very small, we stop and return the root. Otherwise, if the sign change occurs between a and c, then the root lies in the left half, as it lies in the right half. So every iteration cuts the interval into half. That is why the time complexity is logarithmic. O of log base 2 of b minus a upon epsilon. The space complexity is constant O1 because we only store a few variables. The order of convergence is 1, which means a linear convergence. So it is accurate but comparatively slower. Regula-Falsi method. It is also called the false position method. The method is similar to the bisection because it also requires two initial points having opposite signs. But instead of taking the midpoint, it draws a straight line between the 2 points and finds where that line crosses the x-axis. In the code, the formula is C equals A plus f of A multiplied by B minus A divided by f of B minus f of A. This gives a better approximation compared to the midpoint. After calculating C, we again check where the sign change occurs and update either A or B. The process continues until the error occurs is smaller than the tolerance value. Its time complexity is O of n, space complexity is O of 1, and convergence is approximately linear. It usually converges faster than bisection because it uses function values intelligently. Secant method. The method is very important because it removes the need of bracketing. Unlike bisection and Regula-Falsi, here we do not need opposite signs. Instead, we start with two initial guesses, x0 and x1. The method approximates the derivative using the slope between these 2 points. The update formula is x2 equals x1 minus fx1 multiplied by x1 minus x0 divided by fx1 minus fx0. In the code, after computing x2, we calculate the error using absolute value of x2 minus x1. If the error becomes smaller than tolerance, the method stops. Then we shift x0 becomes x1 and x1 becomes x2. The process repeats iteratively. The time complexity is O of n, space complexity is O of 1, and the order of convergence is around 1.618 and also called the golden ratio convergence. So it converges much faster than linear methods. Newton-Raphson method, which is one of the fastest root finding methods. This method uses both the function and its derivative. The Newton-Raphson formula is x nu equals x minus fx divided by f dash of x. Geometrically, this method uses the tangent line at the current point and finds where the tangent intersects the x-axis. In the order, we calculate the function value, then the derivative, then update x using the formula. If the derivative becomes extremely small, we stop to avoid division errors. Finally, if the difference between successive values becomes smaller than tolerance, we return the root. This method converged in only 4 iterations, which was the fastest among all methods. Its time complexity is O of n, space complexity is O of 1, and its order of convergence is 2, called quadratic convergence. Quadratic convergence means the error decreases very rapidly after each iteration. Fixed point iteration method. This method solves equations in the form x equals g of x. In this code, we define g of x equals the square root of x plus 1. Then, inside the fixed point function, we start with an initial guess x0. In every iteration, a new value is calculated using x new equals g of x. Then the error is calculated as absolute value of x new minus x. If the error becomes smaller than the tolerance value, the method stops and returns the root. Otherwise, x is updated and the process repeats. The obtained root is approximately 1.618 for this condition. And now for complexity analysis, the time complexity is O of n because the algorithm performs a fixed set of operations in each iteration. The space complexity is O of 1 since only a few variables are used. The order of convergence is linear or p equals 1, so convergence is slower compared to Newton-Raphson or secant methods. So overall, bisection is simple and reliable. Regula-Falsi improves bisection using line intersection. Secant is faster because it approximates derivatives. Newton-Raphson is the fastest due to quadratic convergence. And fixed point iteration is simple but usually slower. Section 2 is about interpolation. Interpolation is used to estimate unknown values between given data points. In this section, different interpolation techniques are implemented in Python to estimate values and analyze their efficiency. Lagrange interpolation. In Lagrange interpolation, the polynomial is formed using all given data points. In the code, first the number of points is stored in n and result is initialized to 0. Then the outer loop runs for every data point. Inside it, two variables num and then are used to calculate the numerator and denominator of the Lagrange basis polynomial. The inner loop multiplies terms of the form t minus xs of j and xs of I minus xs of j. After calculating the basics polynomial, it is multiplied with the corresponding y value and added to the final result. The time complexity is O(n) square because of nested loops and space complexity is O of n. This method works for unequal spacing. Hermite interpolation. It uses both function values and derivative values. In the code, derivatives at endpoints are calculated using forward and backward difference formulas. For interior points, central difference is used, then repeated nodes and divided difference are used to build the Hermite table. The time complexity is O(n) square and the space complexity is also O(n) square because the table is stored in memory. Newton divided difference method. In this method, a divided difference table is created first. In the code, a matrix F is initialized and the first column is filled with y values. The nested loops calculate higher order divided difference using previous values. During evaluation, the polynomial is formed step by step using cumulative multiplication terms. The build complexity is O(n) square, evaluation complexity is O(n), and space complexity is O(n) square. Forward and backward difference table. This method creates a finite difference table for equally spaced table. In the code, the first column stores the y value. The nested loops calculate successive forward difference by subtracting adjacent terms. The table helps in interpolation and identifying polynomial degree. The time complexity is O(n) square and space complexity is also O(n) square. So equal spacing is required for correct results. Newton-Gregory forward-backward interpolation. In this method, interpolation is done using forward differences. In the code, spacing h is calculated first and checked for equality. Then the forward difference table is generated. The parameter s is calculated using t minus x0 divided by h. A loop then computes factorial terms and successive products to evaluate the interpolation polynomial. The time complexity is O(n) square and the space complexity is also O(n) square. This method works only for equally spaced data points. Section 3. Numerical Differentiation. Okay, so numerical differentiation is used to estimate derivatives from given data points when the exact derivative is difficult to calculate analytically. In this section, two different methods are implemented in Python. Differentiation via Lagrange polynomial. In this method, the derivative is calculated using the Lagrange interpolation polynomial. In the code, first the number of data points is stored in n and derivative value is initialized to 0. The outer loop runs for each interpolation term. Inside the loop, the denominator of the Lagrange basis polynomial is calculated. Then another nested loop computes the derivative part of the basis polynomial using multiplication terms. Finally, each term is multiplied with its corresponding y value and added to the final derivative. The time complexity is O(n) square because multiple nested loops are used, and the space complexity is O of n. The error order is O of h to the power n, which gives good accuracy for smooth functions. Finite difference derivative. This method estimates derivatives using forward, backward, and central difference formulas. In the code, an array named derivs is created to store derivative values. The first point uses the forward difference formula. Interior points uses the central difference formula, which is more accurate, and the last point uses the backward difference formula. Each derivative is calculated using differences between neighboring function values. The time complexity is O to the O of n because the array is transversed once. The space complexity is O of n. Central difference gives accuracy of O h square, which is better than forward and backward difference methods. Section 4 is about numerical quadrature. Numerical quadrature means numerical integration where we approximate the area under a curve using different mathematical formulas. In the section, Newton-Cotes Method and Gauss-Lagrange Quadrature are implemented in Python. Newton-Cotes Formula. In this method, integration is approximated using equally spaced points. The code includes trapezoidal rule, Simpson's 1 by 3 rule, and Widal's rule. In the trapezoidal rule, the interval is divided into small parts using step size h. Then x and y values are generated, and the trapezoidal formula is applied using weighted sums. In Simpson's 1 by 3 rule, odd indexed terms are multiplied by 4 and even indexed terms by 2 for better accuracy. And in Widal's rule, predefined coefficients are used over block of 6 intervals. The time complexity is O of n because all method transfers the interval point once. The accuracy improves from OH square for trapezoidal to OH power 4 for Simpsons and OH power 8 for Widal's rule. The space complexity is On because arrays of x and y are stored. Gauss-Lagrange quadrature. It is highly accurate integration method. In the code, pre-computed nodes and weights are used. First, the interval is transformed from the range -1 to 1 into the required interval using scaling and shifting. Then a loop evaluates the function at transformed points and multiplies them with corresponding weights. Finally, all weighted values are added to obtain the integral. The time complexity is On because only n function evaluations are needed. The space complexity is O1. This method is very effective and gives exact result for polynomials of degree less than or equal to 2n minus 1. Section 5 is about solving system of linear equations. In this section, both direct and iterative numerical methods are implemented in Python to find the value of unknown variables. First is Gauss elimination with partial pivoting. Gauss elimination is a direct method used to solve linear equations. In the code, first the coefficient matrix A and vector B are combined into an augmented matrix. Then forward elimination is performed to convert the matrix into upper triangular form. Partial pivoting is used to swap rows whenever a larger pivot element is needed for numerical stability. After elimination, back substitution is used to calculate the unknown value of variables from bottom to top. The time complexity is O(n) cube because of nested elimination loops. The space complexity is O(n) square since the augmented matrix is stored. This method gives an exact solution in finite steps. Jacobi iteration method. It is an iterative technique for solving linear equations. In the code, the solution vector x is initialized with zeros. For every iteration, a new value of each variable is calculated using only old values stored in xold. After updating all variables, the maximum error is checked. If the error becomes smaller than tolerance, the iteration stops. The time complexity is O kn square per iteration. The space complexity is O of n because two vectors are used, and this method has linear convergence and is easy to parallelize. Gauss-Seidel method. It is similar to Jacobi but converges faster. In the code, updated values are immediately reused during the same iteration. This improves convergence speed. The loop calculates sigma using the latest available values and updates x directly. Then the maximum error is checked for convergence. The time complexity is O of kn square and the space complexity is O of n. Since updated values are used instantly, this method usually converges almost twice as fast as Jacobi method. Section 6 is about approximation methods. Approximation is used when exact functions are difficult to obtain. So we create a function that closely matches the given data. In the section, least square approximation and orthogonal polynomial approximations are implemented in Python. Least squares polynomial approximation. In least squares approximation, the goal is to find a polynomial that minimizes the sum of squared errors between actual and predicted values. In the code, first, the normal equation matrix n and vector r are created. Nested loops calculate sums of power of x values to fill the matrix. The NumPy's linear solver is used to compute the polynomial coefficient. After that, residual and SSE, which is sum of squared errors, are calculated to measure accuracy. The time complexity is OMN square for building the equations and ON cube for solving them. The space complexity is O n square because matrices are stored, and higher degree polynomials usually produce lower error and better fitting. Orthogonal polynomial approximation. This method uses Lagrange polynomials for stable approximations. In the code, the data points are first normalized to the range -1 to 1. Then Lagrange polynomials are generated using Bonnet's recurrence relation. A loop calculates coefficients by projecting the data onto each polynomial basis. These coefficients form the final approximation. The time complexity is O(n) square and the space complexity is O(n). The method is numerically stable and performs well even for higher degree polynomials. Section 7 is about solving ordinary differential equations, also called ODEs. An ODE contains derivatives of a function, and numerical methods are used to approximate the solution at different points. In this section, Euler method, Runge-Kutta method, Picard's method, and Taylor series method are implemented in Python. Euler method. It is the simplest numerical method for solving ODEs. In the code, we start with initial values of x and y. Inside the loop, the slope is calculated using the differential equation function. Then the next y value is updated using y plus h multiplied by slope. The x value is also increased by step size h. This process continues until the final x value is reached. The time complexity is O(n) because calculations are done once per step. The space complexity is O of 1. The global error is OH, so accuracy improves when step size becomes smaller. Runge-Kutta fourth order. RK4 is a highly accurate method for solving ODEs. In the code, four slopes are calculated K1, K2, K3, and K4. These slopes estimate the function behavior at different positions within the interval. Then, a weighted average of all slopes is used to update y. Finally, x is increased by step size h. The time complexity is O of n with 4 function evaluations per step. The space complexity is O of 1. The global error is O h to the power 4, making RK4 much more accurate than Euler method. Picard's method. It is an iterative analytical approach for solving differential equations. In the code, the solution is represented using polynomial coefficients. The function polyintegrate is used to integrate polynomial terms. During each iteration, the current approximation is substituted back into the equation to generate a better approximation. The iteration gradually approach the exact Taylor series solution. The method is mainly symbolic in nature. The space complexity is O of n because the polynomial coefficients are stored. Taylor series method. The solution in in Taylor series method, the solution is expanded using higher order derivatives. In the code, derivatives are calculated up to the required order. Then the Taylor expansion formula is applied using factorial terms and power of h. The loop repeats the process for every step. The time complexity is O of n multiplied by order, and the space complexity is O of order. Higher order Taylor expansion give much better accuracy with smaller errors. So this was my complete presentation for second assignment, and all the methods are implemented successfully in Python along with complexity analysis and result verification. Yeah, thank you for watching.